Welcome to AP Chemistry at Heidelberg High School. I'm Brian Brown, and today we'll be finishing up our notes on Chapter 7. And we'll start with our section 7.6, where we're looking at properties of metals, nonmetals, and metalloids on the periodic table. Now, some of this you should remember from last year, because we talked about in pre-AP Chemistry, where are the metals, where are the nonmetals, and where are the metalloids. Well, one thing we really didn't get into quite as much is why they're in those parts of the periodic table. Now, what is metallic character? So what does it take to be a metal? Well, metals are things that form cations. That means they lose electrons. So that must mean the better you are at losing electrons, the more metallic you're going to behave. And the worse you are at losing electrons, the less metallic you're going to behave. And if you apply the same two principles that we applied basically with everything else we've looked at trend-wise in this chapter, as you go across, it's all about period trends, increasing effective nuclear strength. Well, if you're holding on to electrons harder as you go across into the or to the right on the periodic table, that would mean you should be less metallic, less likely to lose electrons. So as you go to the left, you should be more metallic, more likely to lose electrons. And as you go down, remember within a group, it's not about effective nuclear strength, it's really about increasing N and what that does. Well, as the atoms get larger, those electrons on the outside, by Coulomb's law, are more weakly held onto. So once again, it becomes easier to pull off electrons if you're more weakly held onto. So going to the left, you become more metallic, and going down, you become more metallic. So one quick way to remember it is francium. That bottom left-hand corner are going to be your most metallic substances, which is why as you look at our periodic table, all of the stuff on the left here, those are going to be metallic. The exact opposite would be our nonmetals. Those are going to be things that want to do the exact opposite as metals. And then there's the substances in between that sometimes behave like a metal and sometimes behave like a nonmetal. And those are our metalloids. Now, differences between metals and nonmetals really tend to revolve around these properties and what it means to lose electrons more easily or not lose electrons easily. And we'll come back to most of those properties in a future slide here. So remember, metals are things that tend to form cations, whereas nonmetals are going to do the exact opposite. They gain electrons to achieve a noble gas configuration. Now, when you look at metals, they tend to be lustrous and malleable and ductile. They tend to be good conductors of heat and electricity. And metals, as a general rule, also tend to chemically react in certain ways. Now, one of the things you should be able to predict with metals is how they're going to interact with nonmetals. So remember, metals lose electrons, nonmetals gain electrons. So what we're really looking at here is a simple transfer of electrons between the two until both become stable ions. So consequently, metals and nonmetals react to form ionic compounds. You should be able to use the charges of the ions that would most likely form our metals and nonmetals to predict the formulas that are going to occur. The other thing to remember besides checking the periodic table to see what likely ions they form is remember some elemental formulas are not monatomic, they're diatomic. So remember from pre-AP chemistry, whether it was Hahn-Fickelbrei or whatever technique you used to remember the 7 diatomics, that becomes very important in reaction writing for these simple synthesis reactions. So that's one thing you should be able to do with metals is predict what's going to happen when they react with a non-metal. Other metal reactions you should be able to handle is when certain types of metals or metallic compounds, how they react with water. So that's introduced in this chapter. So metals and metal hydrides do the same thing. They're going to form bases and hydrogen. So remember, these are hydrogen forming reactions. So if you see in the homework or on the test or on the AP test that you have a metal or a metal hydride with water, make a base and also make hydrogen gas and then balance. If it's a metal oxide in water, it's a little bit simpler. All you need to do is form a base. So they all form bases. They share that in common. But the metals and the metal hydrides also form hydrogen. Because what's really happening when the metal, if it's a reactive metal, goes in water is a single replacement reaction where it kicks out the hydrogen, and hydrogen is hydrogen gas. And metal then ends up with a hydroxide, so you form a metal hydroxide, a base. And in the case of calcium hydride, what we have here is a uh, replacement reaction. Um, but in this particular case, you're going to end up with the metal ending up with hydroxide, and your hydrogens left over just are going to form hydrogen gas. Now, nonmetals, on the other hand, tend to be the exact opposite. They're not shiny or lustrous, they're dull. They're not malleable. which means when you hit them with a hammer, they flatten out or ductile. They're the exact opposite. They're very brittle substances. And they're also consequently very poor conductors of heat and electricity. Now, when you put a nonmetal with a metal, remember, as a substance that tends to gain electrons, they're going to react with metals to achieve a noble gas configuration in that synthesis reaction we looked at on the previous slide. So when we're talking about our nonmetals, we're not going to re-look at our synthesis situation. Just remember, metals and nonmetals react together to form ionic compounds. Now, substances containing only nonmetals form our molecular compounds. Some reactions that you should understand with metals are some nonmetals. Nonmetal oxides with water, and it gets more complicated, but the only type you would expect to see on the periodic table would be a simple situation where what we're really doing is combining in essence, a synthesis reaction. So SO2 and H2O, that's going to be one S with three O's and our two hydrogens to form an acid H2SO3. So simply, the type of reactions that I would expect you to be able to handle or that you would see on the AP test or my test with these would be simple situations where you're going to combine them together to form an acid. So just remember metal or non-metal oxides with water, they're going to come together to form an acid. Now in the first case here we had H2SO3, which is not one of our strong acids, so notice we keep it in its molecular form. Whereas in the second case, 1S, a total of four O's and our two hydrogens, well, that's sulfuric acid, H2SO4, which is a strong acid. So if you're writing for equation 4, what it's going to exist as, remember that's going to split to H plus and HSO4 minus. And then the last one, P2O5 plus water. We've got two phosphoruses here. We've got a bunch of oxygens and we have a whole bunch of hydrogens. Well, if we were going to try and make an acid out of that, what type of acid would I form? Well, remember, it's going to have one hydrogen, two hydrogens, or three hydrogens. So I appear to have way too many hydrogens here. So basically look at everything and then just cut it in half. So think of it as making two acids in this case. So instead of two phosphoruses, I'm going to have one. Instead of a total of six oxygens, I'm going to have, oops, um, total, I got to count properly. Three O's and five O's gives a total of eight. So that's going to be four O's. Well, P and four O's, that's phosphate. And then all of our hydrogens then cut in half would be three of them. So that would be H3PO4, phosphoric acid. Another weak acid, so notice it stays in its molecular form when we put it together. So if you had a substance that made, it looks to be way too many hydrogens to form a normal acid, all you're really going to do is cut it in half and look at what's left. These are relatively simple to do. You're just smushing them together and see what acid you get. And remember, if you get a strong acid, like H2SO4, we have to write it broken apart. Otherwise, it's going to be a weak acid. We keep it in its molecular form if we're writing the net ionic equation for them. So for nonmetals, know how they react with metals and also know how nonmetal oxides react in water. Just like we looked at metal oxides in water, we also look at nonmetal oxides in water. So how come we're not talking about nonmetal hydrides and nonmetals in water? It's because they don't really do all that much to react with water. So I don't really worry about their reactions. Now what's left would be our metalloids. Metalloids are things that have properties of both metals and nonmetals because they're right on the border between the two. In some ways, they behave more like a metal. In other ways, they behave more like a nonmetal. For instance, the substance silicon, which is what you see here, it's very shiny, but it's also very brittle and a fairly poor conductor of electricity. So it has properties of both metals and nonmetals. And that's what a metalloid is. And we don't really get into metalloid reactions. We just look at a few basic reactions between nonmetals and metals and then throwing a few types of metal compounds and metals in water, as well as uh, one type particular of nonmetal oxide in water. Now, some trends with these things. Some common groups that are important on the periodic table. First one would be their alkali metals. Because it's a group that behaves so uniformly, it gets a family name. So our group 1 metals would be called alkali metals. And they're really, the name comes from the Arabic word for ashes, because this is one of the first places in which these compounds were formed, or substances were formed. Um, Alkali metals are found only in compounds in nature. They're never found in their elemental form. So alkali metals are so incredibly reactive, they're always going to be in a compound and never found in their elemental form in nature. They also are things that have relatively low densities. I mean, think about it, the whole idea of nuclear strength taken to an extreme here. Well, if you're looking at how compact these things are, um, alkali metals on the far left side of the periodic table with weaker effective nuclear strengths, you would expect them to be held together a little less weakly, so they would drift apart and they tend to have low densities and low melting points. So they're easier to melt and they tend to have lower densities. They also are going to have very low ionization energies. If they hold on to electrons very, very weakly, it's very easy to pull those electrons out. So they tend to have low ionization energies compared to other parts of the periodic table. And one consequence of their increasing metallic character as you go down is as they hold on to electrons more and more and more weakly, then they tend to react much more violently with those things around them. So alkali metals reactivity tends to increase as you go down the group. One common reaction, remember this is just reiterating what we looked at as a general trend with metals. I said reactive metals react with water to form bases and hydrogen. So those reactive metals literally strip a hydrogen from water and you're left with a metal hydroxide, which is basic, and hydrogen gas. Now, alkali metals also have some fundamental characteristic properties of how they look in solution, um, in terms of how they're going to burn. So lithium solutions and lithium compounds tend to be reddish in color. Sodium compounds, remember the electric pickle situation we looked at. We already looked at why those were yellow in color. And potassium compounds tend to be purple in color. Now there are periodically some questions on the test related to um, descriptive chemistry, which would be literally understanding that, oh, it's reddish in color when it burns, so that probably is going to be lithium. It's yellowish, it's going to be sodium. Those are getting less and less and less important on the periodic table, but they still pop up from time to time, so I wanted to introduce just the general idea of the colors some of these would produce when they're in flame, or as a salt dissolved in water, if you burn them, what types of colors you would see. Not that these are going to be heavily stressed on the test at all. Now, second group of note on the periodic table would be the alkaline earth metals. Alkaline earth metals are similar to the alkali metals in terms of many of their properties, but they are higher in density and in melting point than the alkali metals are. They also tend to have higher ionization energies, and all of those things would make sense if you think about the fact that moving to the right, you would increase in nuclear strength or effective nuclear charge. And remember, their ionization energies are low, but they're not going to be as low as what was happening with the previous group. And also notice as you go down, the ionization energies are decreasing. That means that as you go down the alkaline earth metals, they also tend to increase in reactivity as you go down. So all those things are tied together. In terms of their reaction, once again, we talked about how reactive metals, when you put them in water, will make metal hydroxide, so a basic solution, and hydrogen gas. So these things will fundamentally do the same things the alkali metals, but because you tend to form different charges, you're going to end up with a slightly different balanced equation. But they behave very, very similar. Now, one exception to this would be beryllium. Not that you need to know this for the test or the AP test, but beryllium doesn't happen to do that. And it makes sense if you think about why. Remember, as you went down, they increased in reactivity. So at the top, you would have the least reactive situation. So beryllium is not reactive enough to actually react with water. But if I ask you about a metal thrown in water on the test, always, 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 or on the AP test, predict you're going to make a base and hydrogen. Next group, we skip across a little bit here and we get to group 6A, which is the oxygen group. Now, as we move down the group, our metallic character increases. So oxygen and sulfur and selenium would be nonmetals. But as we move down, we start to get away from non-metallic character and we get into more metalloid or metallic character. So that makes this a unique group. Tellurium is actually a metalloid, and radioactive polonium, which would be at the bottom, would actually behave like a metal. So now we're looking at a group of elements that really have very different properties you go down, and it's because we're right on that break line between metals and non-metals. And consequently, if we talk about things in this group, we tend to talk about individual group, or I should say individual element properties rather than properties of the group as a whole. A couple things about hydrogen. There's two fundamental allotropes of hydrogen, O2 and O3, which is ozone, something you should remember hopefully from pre-AP chemistry. Sometimes we look at that. But ozone is not as stable as oxygen. So around us, when we talk about oxygen, we're talking about oxygen gas, O2. And there's three fundamental ions that oxygen form. Now, the one that we deal with most often is oxide. So unless you're ever mentioned, unless you're given any specific information like hint, it's a peroxide or it's a superoxide, you always assume that what's going to happen is we're going to deal with a oxide is the 2 minus anion. So unless you're given any other information, like in the case of the brown bottle on your medicine cabinet shelf that's called a hydrogen peroxide, that would tell you that what we're looking at here is the peroxide form, and that would be O2 2 minus. Remember, hydrogen with a nonmetal is a plus 1, so that would mean we would need two H's to mix with this to give a neutral compound. So that would be the formula of hydrogen peroxide. This isn't something you have to do a lot of, but just be aware that there are different forms of the anion oxygen. But the most stable one, the most prevalent one, the one you're going to see if it doesn't say anything different, is it's going to be oxide. And remember, oxygen are things that take electrons from other elements, so they're oxidizing agents. They cause oxidation, which is really where the term oxidation comes from, because our earliest understanding of situations where we have electron transfers and reactions with oxygens would be oxygen reacting with a metal, in other words, corrosion. Um, when that metal rusts as it reacts with oxygen is stealing the electrons from the metal to become stable. So our actual terminology with oxidation numbers and oxidation reactions and redox reactions that really began with an understanding of oxygen as it would react with metal. But oxygen is something that's a great oxidizer. It's very good at stealing electrons. Once again, if you look at where it's on the periodic table, it makes sense. It's over to the right and it's also high up. So that means it should be good at grabbing electrons from things. Now, sulfur one down is not as strong of an oxidizer. And once again, that would make sense. It's a little bit farther down the periodic table. It's not going to be because the nucleus of sulfur is greater, farther distance away because of increased N. So it really shouldn't be quite as good at grabbing electrons from things. So you'd expect sulfur to be a weaker oxidizing agent. And one odd thing about sulfur is the most stable form of sulfur is not actually monatomic sulfur. It's actually a ring of 8 sulfur molecules put together. Next group over, halogens. Once again, like alkali metals and alkaline earth metals, a very predictable group. So they are our typical non-metal substances. Unlike oxygen and sulfur, that family, as you went down, they're becoming less and less like non-metals. Well, the whole halogen group would fit into our fluorine, chlorine, bromine, iodine, are very non-metallic things. Um, the actual term for halogen uh, comes from halos, which deals with salt formers. That's what these things do. When they react with metals, they form salts. Halogens have very large negative electron affinities. Therefore, they tend to oxidize other elements very easily. They tend to be great at stealing electrons and causing reactions. So they can react directly with metals to form metal halides. Remember, I said earlier you should be able to predict metal and nonmetal reactions. Well, this would be an example of that. And one common use of on halogen in everyday life that is really important to us because it helps keep our drinking water safe is that chlorine can be added to water and it can serve as a disinfectant. It can kill minute quantities of bacteria and so forth that can be in there. So those smaller organisms would be affected. Larger organisms like us would be unaffected. And the last group of note on the periodic table would be the noble gases. And remember, noble gases are inert gases at the far side of the periodic table. They are substances that tend not to react with anything else on the periodic table. So notice they have very high ionization energies. So noble gases have very large ionization energies. And their electron affinities, unlike the rest of the periodic table in general, are positive. So therefore, they're relatively unreactive substances, which gives them their name. The noble gases don't react with commoners and the gases around them. But they are found in some non-metallic monatomic gases. And there are a couple of different compounds that form with our noble gases. So one of the things from pre-AP was we basically said, noble gases never react. Well, that's not really true. There are some compounds that can form. They're just highly unlikely to form. And if you look at what substances would tend to do it, well, it should be the substances that, you know, have by where they're at in the periodic table, the substances farther down on our list because those should be made more easily to interact their electrons with others. So you'll notice when we look at what types of compounds can actually form, well, it's a relatively small group, and one of the most common noble gases to actually form compounds would be the xenon group. Now, radon, radioactive gas, we don't really worry about it hanging around enough to deal with and make chemical reactions. So, but we can make stable compounds from xenon because it's the farthest down the list, which would mean next up, krypton should maybe be able to form. Well, it does, but at this time we only know that it forms one stable compound. And above that, we don't know of any stable compounds that are actually formed. So noble gases are things that are relatively non-reactive, but the reality is if you're down far enough on the list, you can have slight reactivities. So with the right element, notice we're dealing with fluorine here, the most electronegative element on the whole periodic table, we can form a few stable compounds with a few of our noble gases. And finally, there is, I guess, one unstable, not stable, but an unstable compound that was formed in 2000 with argon. But the key word there being it's an unstable compound. So by and large, noble gases don't form compounds with much of anything. So that ends our notes on chapter 7.